Dear committee, thanks for watching my presentation. My name is Meng-Chi. I'm Professor Zhou Pi-Tai's master student. I'm curious about the phenomena. Weak fluorescent phenothiazine has a quantum yield less than 1% in nonpolar solvent. However, substituted C3 position with a nitrile group, a commonly known fluorescence quencher, the resulting 3-nitrile phenothiazine has a quantum yield 100% in nonpolar solvent. And why is that? Here is what we know in the early stage of the research. In 5 common solvents, PTZ has a quantum yield less than 1% in all these solvents, but PTZNO2 can achieve 100% POQI in cyclohexane. This is very interesting because nitrile group is a common fluorescence quencher and phenothiazine is non-fluorescent. To gain insight into this paradox, a series C3 substituted phenothiazine from electron-donating methoxy group to electron-withdrawing nitrile group was designed and synthesized. We combine steady-state and time-resolved spectral data to analyze their photophysical property. On the right-hand side are 2 figures of absorption and emission spectrum in 5 solvents. There is an obvious trend from local excitation of PTZOMe to charge transfer of PTZNO2. Additionally, the radiative and non-radiative decay rate constant gave us some clue in explaining the difference in the fluorescence. For PTZOMe, the radiative rate constant is about 10 to the power of 6. For PTZNO2 in cyclohexane, the radiative rate constant is about 10 to the power of 8, which is very high. Computational approach were also conducted to elucidate their ground state, excited state, optimized structure, as well as HOMO-LUMO orbitals. In addition to analyze their penalization chain along the NS bond, we found that sulfur's lone pair electron plays a key role in the electronic transition. Using PTZ and PTZNO2 as example, the LUMO of PTZ is not a pure pi antibonding orbital. It's mixed with non-bonding orbital from the sulfur atom. On the other hand, the LUMO of PTZNO2 is a pure pi antibonding orbital. This implies that the transition between HOMO and LUMO of PTZ is a partially forbidden pi to pi start mixed with non-bonding orbital, and the PTZNO2 has allowed pi to pi start transition, therefore it's highly fluorescent. Cyclic voltammetry analysis were also conducted to verify the intrinsic electronic property of PTZ and its derivatives. Rationalization or transformation from local excitation to charge transfer may be offered in a quantitative manner based on the Markov's rule to deduce the free energy of charge transfer in the excited state. For example, local excitation dominant PTZOMe has the most positive free energy of charge transfer, which means that charge transfer is highly unfavorable in PTZOMe. For PTZNO2 with the most negative free energy of charge transfer, it means that charge transfer is highly favorable in PTZNO2, and we can see that from the spectral data. In conclusion, PTZ and PTZOMe exhibit partially forbidden transition because their pi start is mixed with non-bonding from the sulfur atom. On the other hand, introducing electron withdrawing groups lower the energy level of LUMOs and diminish the mixing of non-bonding orbital with the pi star orbital. Therefore, PTZNO2 exhibit a brilliant photophysical property with a quantity of 100% in cyclohexane. Thanks for your attention. Have a nice day.